Here's a recap of today's limiting reagents lab. Step 1 was to add 100 milliliters of 1 molar hydrochloric acid into each of your flasks. So here's your setup. I got my hydrochloric acid, which I labeled as moles per liter, in case that might have helped you with your stoichiometry. I'm going to try to do all this with one hand, and got a graduated cylinder. I labeled my flasks so it's easier for you to follow in this video. Looks like that's at the bottom of the meniscus. I'm at 100. Add that to my first flask. So I got 100 mils in that flask. I'm going to repeat for my other two flasks. I spilled some hydrochloric acid, so I had to clean that up. But now I have 100 milliliters of hydrochloric acid in each of my flasks. Next up, we're going to mass 0.7 grams of magnesium and put it into a balloon. 1.4 grams of magnesium, put into a second balloon, and 2.4 grams of magnesium and put that into a third balloon. Turn on the scale. Let that calibrate. I'm going to use a small beaker, so I'm going to zero that out. .70. I really couldn't do the next step. I really couldn't pour it in here with one hand, so I got the 0.7 grams of magnesium in that balloon. I'm going to get 1.4 now. Nice. So I transferred the 1.4 grams of magnesium into that second balloon, and now I'm going to get 2.4. Ooh, good enough. So I got my 2.4 grams of magnesium in that third balloon. In our next step, we're going to put these balloons over our flasks. And obviously I'm going to need two hands to do this step, so I'll be right back. So I successfully got the balloons over all of my flasks. Let's move this guy out of the way, lower the hazard, lower the risk. All right, so now it's time to start the reaction by getting the magnesium, all of that in there. And if you feel these get very hot. So while we're waiting for this reaction to finish, let's go over the stoichiometry. Actually, before we do that, we can, because we know it's releasing heat, we can draw the potential energy to the reaction progress diagram. So we have our reactants. In this case, we have magnesium metal, and we have hydrochloric acid, and there's going to be some amount of activation energy. And since the delta H, or the change in energy here, is negative, this is an exothermic reaction. And the products, this is a single displacement reaction, so the products are going to be hydrogen gas, which is what we're collecting in the balloons, and magnesium chloride in solution. There's your activation energy. All right, let's balance this equation so we can do the stoichiometry. So we have 2 chlorines on the product side. We need a 2. And that looks like it doesn't. Now we can do our stoichiometry. We want to know, before we start, we already started, but before you started, you wanted to predict how much hydrogen gas will be collected in these balloons, given these reactants. So notice they all have the same number of hydrogen chloride. So let's do that first. Actually, let's just convert that to liters, so to save a little space. Now, the number of moles in that, because it's 1 mole per liter, that was the concentration given to you. Now we can convert that to, now we can use the mole ratios to see how much hydrogen gas is produced. That's from the mole ratio. We're going to assume we're close enough to STP, and therefore the conversion factor we'll use is the molar volume. Shucks, I don't have a calculator. Let's see, we don't need a calculator. All right, because half of that is 11.2. And then we're going to divide that by 10. So it is 1.12 liters. So that's how much hydrogen gas we could make if we had no limiting reagent in it. We only had 100 mils of 1 molar hydrochloric acid. So now let's take our first scenario, 0.7 grams of magnesium. Convert that to moles. Actually, I'm not going to do this for you. You do the rest. But I'll help you set it up. So convert to moles. Right. And then use that. Now use the mole ratio to convert from your reactant magnesium to the product. It's not always the product that you're looking for, but in this case it is. All right, so you fill these, you figure these out. Show your work. Now you're going to see when you do that, there's going to be a limiting reactant. In other words, because of one of these reactants, you're not going to be able to produce as much hydrogen gas. So you got to figure out which one that is by seeing which produces less. That's going to be your limiting reactant. And do this, repeat this 2 more times for the other 2 scenarios. Then you should have predicted that this balloon is going to be the smallest. So whatever liters it is, you should get that from your stoichiometry. And this balloon should be roughly twice as large, because I set it up where in the first scenario, this runs out first. All right, so you got to know what that's called. Now in the second scenario, I gave myself a little bit margin error, and if I had 1.2, it would have been very close, but I wanted you to put a little bit more in there just to make sure that these 2 balloons would end up be the same. All right, so the limiting reagent was the hydrochloric acid in this one, in the second one, but not by much. There shouldn't have been much magnesium observed in your flat, a little bit, but not a lot, like 0.2 grams, which is barely noticeable. Now this last one, you're going to clearly run out of this guy first. You should see a lot of magnesium left over in your flask, but that shouldn't have changed the size. So I'll let you figure out you're going to have to do your stoichiometry to get the volumes of these balloons. Looks like the reaction is done. I don't know how clear it is or easy it is to see in a video, but it looks pretty good here. This is the smallest balloon, and these 2 are about the same size, being roughly almost double that one. And if we look here, there's no magnesium left in the first flask, and there's none there in the second one, and there's excess magnesium in the third one.